Thank you all for tuning into the Taiwan Space Union CubeSats webinars. This is our first talk for today. Our first talk is Dr. James Mason, who's a research scientist at the University of Colorado Boulder. And today James will be talking to us about 24 CubeSats launched from CU Boulder. So James, whenever you're ready.
Yeah, thank you. Thanks everybody also for coming to my talk and to all the subsequent talks to come. So I've worked on something like 20 CubeSats so far to date. Some of those are the ones that I'll show you at CU, and others are scattered all over the US and the rest of the world. But I'm only going to be able to talk about a very select few of those in this talk. So these are the ones that CU, University of Colorado Boulder's CU, has launched or will be launching soon. And I just created this timeline today, actually. And I was kind of surprised. I paused when I finished and was like, whoa. You could see where it came, all these data came from in the bottom right where I have the website. So if you want to learn more about anything I talk about today, that's a good place to start. But you can see the white vertical line here. That's today on the timeline. And historically, we've been doing basically one mission at a time. The one exception was the most recent launch where we had a mission called Minx-2 and CSIM launch on the same rocket. And were deployed at exactly 20 minutes apart or something. And they were both using the same communications frequency for uplink and downlink. So worst case scenario, same orbit, same launch, same frequency, but we figured out a way to make it work. But on the right side of this vertical line of today, what's coming in the future, you can see that we're about to get very busy dealing with many missions, all with overlap on top of each other. So that's actually a challenge that we have known is coming for a while now, but just visualizing it like this, really, I sent this around to the group here at CU, and everyone was like, okay, yeah, it's time to really get to work preparing for all this stuff and automating the mission operations to a greater degree than we already have. So that's mainly what I'll say about this timeline. I'll talk now about details about 8 of those missions. There were 24, 25 or so missions listed there, but I can't talk about all of them in any level of detail. So I picked out 8 that I'm the most familiar with to tell you more about in terms of what instruments are on board, what technology they're leveraging, and lessons that we've learned or applied throughout them. So the second CubeSat we ever did was called CSSWE. It's the first one I had any involvement in, and it's the first one that was primarily run by graduate students. The only previous CubeSat we did was called Hermes, and that was done through a program called Space Grant, which was all undergraduate students. So for CSSWE, the Colorado Student Space Weather Experiment, it was a 3U CubeSat. Development for it began around 2009. It then launched a few years later in 2012. It operated until the end of 2014. And if you heard any of the conversation before the talk started, it actually operated until about 2013 and then disappeared. It just stopped communicating with us, but the primary science mission was over and everything. So everyone was disappointed that it had gone, but it wasn't too big a deal. So they did the whole fault tree analysis to try and figure out what went wrong. And then several months later, it just came back to life on its own. And the way that happened was there was a single event upset on the spacecraft that caused an extra amount of power draw on one of the subsystems that drained the battery all the way down during an eclipse. And that caused the battery to disconnect itself when it hit the protection circuitry from the rest of the spacecraft and caused the whole system to reboot. And when it rebooted, everything was okay again. It started beaconing, and they had like another year on orbit of collecting data and normal science operations. So that was just like the one case where a single event upset actually works in your favor. So everyone was very happy, and it was like a phoenix rising from the ashes. And that mission was super successful. It even had a paper in Nature. So it was very high scientific output for any kind of mission, but particularly for a CubeSat. The mission, or the instrument that was inside of it, was a miniaturized version of an instrument on the Van Allen probes called REPT, which collects in situ energetic particle measurements. And the Van Allen probes were in an equatorial orbit. And at the same time, we launched this CSSWE CubeSat to collect basically the same data, but from a highly inclined orbit at 65 degrees, so that we could get complementary measurements from the two Van Allen probes and CSSWE at the same time at very different locations, so you could see particles moving throughout the magnetosphere and from the equator, and then as the particles stream in towards the poles that we could observe with CSSWE. So that Nature paper was like combining Van Allen probes REPT with CSSWE. They called it Reptile. It was the same acronym, but integrated little experiment they added to the end of REPT to make it the instrument for CSSWE. So that was a very successful mission. Everyone was happy with that. The technology inside of it was simple, and it was our second CubeSat, but really the first one that started us on this long trajectory towards building more and more and more of these things. We used a lot of standard stuff for CubeSats. So we used the PC-104 stack, and everyone that worked with it at the time did not enjoy that, and the lesson from it was not to use it again. So you'll see in future slides we stopped using it, and the reason is like what's shown in this picture. Basically, like if anything goes wrong with one of the boards, you first have to slide this standard pumpkin structure off of the entire structure. And then if you want to get to any of the boards, you have to undo the entire stack and then get to the component that you need to test, which is just really cumbersome, especially in these CubeSats where the projects are relatively small and they need to be scrappy, and there's a lot of debugging that goes on. So it's a frequent annoyance to have to deal with that. It used the AstroDev Lithium 1 UHF transceiver, which lots of CubeSats have used. We still use it on some of our missions today. It's worked all right, though we've always had niggling and different kinds of issues with it, so we are starting to move away from it on the upcoming missions that we have. But as a cheap radio to get the job done, I would say we've been happy with it overall. And then CSSWE also did a custom passive attitude control system, which was actually the primary PhD thesis of the person pictured here, David Gerhardt. So it's basically a bunch of magnets and hysteresis rods to dampen the pointing. So it's totally passive, and that worked for the science case. Again, they're looking at energetic particles that are streaming around Earth's magnetosphere, or the magnetic lines. So it made sense to have an attitude system that also aligns your spacecraft with the magnetic field of the Earth, because what you're trying to observe is also going around those magnetic lines. So it was a happy place to find ourselves, where there weren't any commercially available 3-axis control systems at the time, and for this science case, we didn't need one. And again, the mission was really successful, so that worked out. Okay, so that's CSSWE. The next mission we did was MINX-1, also a 3U, the miniature X-ray solar spectrometer, and this is the one that I've been most heavily involved. And you'll see, I've got overlap here, but you'll see in the bottom right the attribution. I wrote a ton of papers about this mission. I think almost every year since 2016, I've been publishing a paper on MINX things, and most of those have been engineering oriented. So if you want to learn more about MINX engineering and on-orbit performance and stuff, there's a lot of papers out about it. So MINX began development in 2011. It launched at the end of 2015 to the International Space Station, which you can see the deployment photo for up here. MINX is this one that's up in front It operated until 2017 May. The instrument inside was a COTS detector to measure X-rays. The COTS component is normally meant to be used for geology, like a little handheld device. So not intended to go into a vacuum, basically. And so we had to do a little bit of modification to make it vacuum compatible and still operate well. But really pretty minor stuff. Yeah, and the orbit, of course, it launched from or deployed from the International Space Station. So that's the orbit it was in. And the mission ended in 2017, not because it stopped working or anything, but just because atmospheric decay had brought it down to the point where it burned up. And we were still getting beacons from it like minutes before it burned up at like 165 kilometers, I think is the last beacon we received from a ham operator in Australia. So that was really exciting, just watching a satellite operate at those altitudes where we were seeing temperatures above 100 Celsius and it was tumbling out of control, but still beaconing fine. So that was fun. Also, this deployment photo was taken by an astronaut looking out the window of the space station, and they took a bunch of photos. And the side of the spacecraft that's facing the camera is actually a side-eye laser engraved with everybody's name. So if you pull like a movie style zoom and enhance, you can see the laser engraved at the end there. Of course, I faked that video. You can't actually see it. It's all blurry, but that side of the spacecraft really does have the laser engraving with everybody's names on it, which is pretty cool to have seen. The technology on Minx is, so we left behind the PC-104 stack as the next step, the lesson learned from CSSWE, and instead went with what's standard practice anyway for all the instruments at LASP and CU that we build, is to have a backplane and then daughter boards that plug into it. And then also for the structure to be basically like a five-sided box, and you can remove the back plate to slide those cards out, and you can see what that looks like in these photos here. So this is the back plate removed on these two versions, and the daughter boards are here, so you can easily slide them out and slide them back in and as needed without having to disassemble the entire thing. We still used the AstroDev Lithium one on this mission because it seemed to work okay for CSSWE. And this was, we upgraded to a 3-axis pointing control because at this time there was a commercial 3-axis control system just coming onto the market. And we were the first flight, Minx 1 was, of Blue Canyon Technologies Exact, which is now widely used all over the place and always growing more expensive as well, because it's so successful and it works really well. And we saw there's a paper out that I published on this as well, which showed that we were getting 15 arc-second 3 sigma accuracy of the pointing performance, which was actually better than the specification sheet, which was great, especially for a first flight. So we were really happy with that as well. Another thing we did on Minx was we did this on CSSWE also, build our own solar panels, but CSSWE did it the traditional, the way you're supposed to do it, where you weld the solar cells to each other. These tabs weld to the backs of the adjacent cell. Instead of that, we solder the cells tabs onto the PCB so that if one of them breaks, you can just take that one cell off and replace it, because these cells are not cheap, for at least on a CubeSat budget. It's a significant expense, so we wanted to be able to replace them if we needed to. And there was one case where we did have a cell break and we did have to replace it. It's also very cumbersome once you have a long string of cells that are all welded together to move them, and because they're so fragile, that's takes a lot of care, and it's an expensive mistake to make if something breaks there. So that was a lesson from CSSWE that we applied here, and we've been doing it on all of the missions we've done since. Is we either just buy the panels outright, but more often we do this because it's pretty cheap to build your own panels and just solder them to the board. And this video that I'm showing is just, it's probably choppy on your end, but you can find it on YouTube. If you just search for making of Minx, and this is actually like a small clip of a 5-minute long video that shows all sorts of things we did beyond the solar cells, how we tested the attitude pointing control system, etc. I'm not actually going to ask you for responses here, but I love asking this question of audiences of trying to find the mistake here. So this is a mistake I made when I was building the battery boards. And in between these two steps, I was taking pictures of every step, which was good practice because we were able to figure out what happened here. But I did something stupid here, which was to take this resistor with its wires exposed and then lay a piece of aluminum foil on top. And that was fine for months during the bench testing, and even once we integrated this battery pack into the spacecraft. But when we put it into the vacuum chamber and all the air was sucked out, this aluminum foil was sucked down onto the electrical leads here and shorted the battery, which, because these were being run off the bus voltage, meant that the entire spacecraft couldn't boot up. So if we hadn't tested for this, it would have gone on or launched from the space station. We never would have heard from it. So seemingly not that big of a mistake, but turned out to could have ended the mission before it even began. But the positive lesson was that, like, I did take these pictures of everything. So when we put it in the vacuum chamber, we were able to go back to the photos and figure out that this was the problem, swap it in with another battery pack I had already built, that I didn't make this dumb mistake. And a few hours later, we were back in the vacuum chamber and everything was fine. So photo documentation can really be a lifesaver. A few years later, we launched Minx 2, which had some improvements to Minx 1. Minx 1 was already successful, but we had built these two satellites at the same time anyway. So we took things that could have been better on Minx 1 and applied those to Minx 2. But unfortunately, like a month after it was deployed from a rocket launch, it stopped communicating with us. And I can tell you why and all the details if you're interested, but in the end, it stopped working. That launch was at the end of 2018, failed a month later. The instrument was the same thing, but an improved version from the COTS vendor that had higher dynamic range and greater spectral resolution. And the orbit was also different. So now we were in a sun-sync orbit at 550 kilometers. And one of the things we improved, which I'm going to talk more about in the next slide, but the photo is here, is that for that AstroDev Lithium-1 radio, inside this blue outline here, it's that aluminum block there. This time we added this copper strap in the green boxes, 2 copper straps going to a copper block that we bolted onto the back plate of the spacecraft that was acting as a dedicated radiator, because the radio could get really hot on Minx 1 and then it would get a little bit finicky when it was trying to downlink. So adding this copper heatsink to it made it so that instead of raising the temperature 30 degrees when we would transmit for like 10 minutes, it would only raise it by 3 degrees. So we hoped that that would help the radio operate better. So a lot of the improvements we made to Minx 2, the intent was to improve the amount of data we could capture back down on the ground, because we generated way more data than we could downlink on our UHF downlink. So the higher altitude meant we were going to have a longer life, except it actually ended up failing after a month, but it would have been like 5-year mission or longer. The high inclination meant that we could build a second ground station in Alaska at high latitude, so that we would go from having only 6 passes a day in Boulder only to having 12 passes a day in Boulder and Alaska. So that's a big increase in the amount of data you can downlink. We also increased the baud rate on the radio from 9600 to 19.2. So we would have gotten a lot more data that way as well. Talked about that heatsink heat strap already for the radio, which would have helped a little bit with getting more data, but mostly it was just, it's not good to see the radio getting that hot. And then we also added flight software for stored commands to execute at specific times on Minx 2. And you can see that this photo on the right is the ground station that we built in Alaska. Okay, some other missions. So after Minx, we built the CSIM, which is a 6U now. So we started getting bigger. CSIM stands for the Compact Spectral Irradiance Monitor. Development for that began around 2017, launched in 2018 at the same time as Minx 2, that same rocket. It's still operating today, so extra sad for Minx 2. We could have still been flying, or working years later. The instrument on this one is a miniaturized version of the bigger instrument that's on the source spacecraft called SIM, which is a spectral radiance monitor. And it's composed of mirrors and prisms and photodiodes and bolometers looking at the sun to get spectra. Same orbit as Minx 2, obviously. This is what the spacecraft looked like during testing. Got way more solar panels than we've had on any of the previous missions. The technology on board. So this is the first flight where we went basically full COTS on the bus. We bought a Blue Canyon exact bus. So instead of just the attitude system from Blue Canyon, we bought their whole bus, and then we just put our instrument inside of it. We've done that for one other mission, but that still hasn't launched, but is launching this year. But everything since then, we're building our own in-house bus, but still using the Blue Canyon attitude system because attitude control is really hard. But everything else, like we are already good at it. So the new bus that we have for 6U CubeSats is basically taking Minx and just having professional engineers design it instead of students, and Tom Woods, who was the PI of this thing and is an enthusiast, I would say, with electrical design and flight software. And obviously the missions worked pretty well, so he did a good job. But now we've got a bus that's like all professional engineers, and we've got better redundancy and rad hard parts, etc. CSIM was also the first time we've done S-band downlink for LASP CubeSats, and as part of that program, we've built now also a 4.2 meter dish on the ground so that we can get something like 1 megabit per second downlink. And every program that is coming up in that timeline, where all of them are using S-band for downlink now. Like I said, for Minx, we built another UHF ground station to get more data back, but really that doesn't take you that much farther. Going to S-band is a huge increase in the amount of data we can get back. Another couple missions. Now I'm collapsing two into a single slide. Maxwell, which is another 6U, and CU E-cubed, another 6U. These are technology demonstrators being developed in the aerospace department at CU. Development for those began around 2016. Launch is expected, at least for Maxwell, later in 2021. CUE cubed, though, as you can see at the bottom here, is going on the SLS rocket that NASA has been building for a long time now, on its inaugural launch, the Artemis 1 mission. So CUE cube's ready to go. We're just waiting on the rocket to be ready to take us. That'll bring CUE cubed into cislunar space. Maxwell will just go to LEO, however, so it's a more reliable launch, or LEO launches happen all the time, so we could be pretty confident that it will happen this year. And the technology on both is this X-band reflect array. So you can see it's got this feed horn, this thing in the front that transmits out this way onto this big square thing. That's the reflect array to give you like really good link margin on the ground in X-band. So we're trying to step up the amount of data we can get back from CubeSats even more, and from far distances as well. So CUE cubed is designed as part of a competition to prove that you can get X-band high bandwidth data back from like deep space on a CubeSat. Another couple CubeSats, another 2-in-1 slide. The CubeSat is a 6U, and the Sprite is NASA's first 12U for astrophysics. I think it'll probably be the first 12U in any science division. So these are both astrophysics CubeSats. Qt will launch later this year, and Sprite is scheduled to launch next year. On Qt, well, they're both use UV spectrographs. On Qt, it's using a CCD to count the photons, and on Sprite, we're using a microchannel plate to count the photons. They'll both go into LEO, and very different astrophysical targets. So CUTE is looking at exoplanet atmospheric composition, escape rates, and magnetospheres, which magnetospheres is a really big deal because that's not something that we have for exoplanets, even from big missions. And SPRITE will be looking at galactic dust and gas and ionizing radiation and how those are modulated by star formation and supernovae in other galaxies. So very far away stuff. Yeah, so those are both really cool, and they are only now possible because of the technology advancements that have been made over the last decade, 2 decades. And this is my concluding slide that's really making that point. So across all of CubeSats and smallsats, but particularly at CU and at LASP, these key challenges are things that we've been working on improving over time. So the first one is the high precision pointing control. So we went from that passive control system to now just fortunately having a COTS vendor where we can buy it. And Blue Canyon is in Boulder as well. So we've worked with them very closely on the development of the system and how it's performed, et cetera. And I really like this quote by Nancy Grace Roman, who's the mother of Hubble Space Telescope. In 1980, during an interview, she said that pointing has been the pacing item that has really controlled what we've been able to do in space astronomy as the field has developed. And that's for the big missions. So it's the same problem, a lot of the same problems that big missions had in early days are the same problems we have to solve in the small sat technology as well, as that world has been becoming more prolific. Another one of the problems is downlink rate. So you can see I talked about us building more UHF ground stations and now going to S-band and starting to develop things for X-band. There's even talk beyond LASP, but a little bit at LASP as well, of doing laser communications to get truly phenomenal downlink rates, like in the gigabit range, which is crazy because that's like internet speeds from a satellite. And then also reliability. So mostly we've been pretty scrappy, and it's like CubeSats are going to fail and you can accept that. And we've had failures as well on our past missions like Minx 2. But as we move forward with each subsequent mission, we're moving, like I said, to more things where we do include a little bit of redundancy. We do start including rad tolerant parts and rad hard designs as much as possible, while still striving to keep the mission cost as low as possible. And then also mission operations, which I don't know if that's been one that's talked about a lot, but at least we've seen it, that automation makes a big difference, so that everyone working on the project can spend their time working on like what targets should we observe, especially in astrophysics, rather than the day-to-day grind of just routine operations. And that's going to become, like I said, a special challenge for us moving forward as we start operating many missions at the same time. Getting all of that to work smoothly is a challenge as well. So yeah, it's no one mission, this bullet point here. The point is really that it's no one mission where we tried to do this everything all at once. It's been incremental. Through each mission, we've increased things and improved upon these things a little bit. And now we've really reached the point where I think most of these key challenges have been mostly solved. And so our near term has those many missions that I showed you on the first slide, which I'll now show you again to conclude that we've got a lot of missions we're going to have to be flying, and it's due to the incremental improvements we've been making over the last decade to all these missions. So I'll stop there, and thanks.
Thank you very much, James. Looks like you guys have a full plate ahead of you guys.
Yeah.
And if I understand correctly, you've recently received funding from NASA for a new mission on heliophysics.
Which one?
Shucks, I forgot the name. I recall seeing it on Facebook.
Oh, I don't know. There's one I'm PIing, and we're still waiting to hear back.
Okay, so you're still in pre-phase A at this moment?
We finished phase A and submitted that in December. We submitted the step 2 proposal in 16 months ago, and we still don't know if we'll get to fly. So fingers still crossed. The next round of proposals is due in 2 weeks, so I'm already basically done with that proposal, but I'm still hoping I won't have to submit it because we'll hopefully get selected this time. That mission's called Sunset.
Okay, so this is under NASA. Just out of curiosity, how does project management work under NASA for a CubeSat mission? So you go through different stages of proposals, and then once you're funded, do they hold reviews? Do you have a dedicated project manager telling you to deliver ASAP, or how does it work?
So that's another interesting thing that's changing. So also on this vertical dividing line, all the way up on the left, it's always been NASA sends us the money and we send in an annual report saying like everything's fine. This is what we did this year, and that was really the only level of oversight we had from NASA. On the right-hand side of the line, they're moving us much more to like the bigger missions where there's monthly telecons we do in addition to the annual reports. They have design reviews that are gates. So if we fail those reviews, which is unlikely, but if we did, they could cancel us. And so basically NASA is becoming more hands-on, and the budgets have been increasing accordingly. So back in these days, the budgets were like $1 million US. In the future, they're more like $5 million or even more. The budget cap is like $14 million or so. So yeah, more oversight and more dollars.
Okay. Well, I guess that's a plus as opposed to oversight and fewer dollars.
Yeah.
From your experience, how much hands-on oversight does a project like this need, especially if you're executing it with primarily a student team?
Primarily with the student team, I think there should be a decent amount of maybe, I don't know if I call it oversight, but just mentorship. And I mean, I came up as a student through all these things, and I didn't know anything about hardware. And I mean, now I know a lot of things, and it's because of experts in electrical engineering, and mechanical engineering, and systems engineering, and project management, etc. I think it helps to have people, professionals that are knowledgeable about these things and are interested in working with students, because then those sorts of things will just happen.
Fair enough. One thing that I have noticed, just since we're just starting with the whole CubeSat project thing over here, is basically oftentimes everyone's really enthusiastic, but in doing so, oftentimes people tend to skip on certain important steps, like you mentioned, documentation every step of the way, or just double checking and triple checking. And do you, based on your experience, how do you guys deal with that? I mean, is there someone literally standing over your shoulder the whole time, or?
So I feel like so far that's for us, it's been hit or miss, and it's really been luck of the draw on whether or not the project has had typically a PhD student that's willing to, wants to stick it out through the long term. So like my own experience, like I knew I was going to be working on this thing until it launched, and I knew that my future self would hate my present self if I wasn't taking lots of photos or documenting things really well, because I was going to be the one that was going to suffer for it. So that was my motivation to do a good job on those things. And when projects don't have that, then yeah, it's not very fun to have to write reports up. It's more fun to be in the lab playing with the hardware. So I don't know if there's like a good way of like incentivizing it, but we've had requirements that all students at the end of every semester submit continuity documentation. That's like a part of their grade if it's in the class, or like, yeah, that's it. That's really been the only stick we've had to enforce such things as grades. And that seems to have been working pretty well, at least for continuity across like a few months. But over years, I don't know what to do other than have somebody that's wanting to do documentation. Fair
enough. Do we have any questions from the audience to James about anything that you heard, or any of the missions that they've executed? If you do, please feel free to speak up. You'll have to unmute yourself.
Hello, this is Christian Fuchs speaking. What's past 2024 for you guys? I mean, I see a lot of planned and ongoing developments until 2023, half through the year, but then what are you guys up for?
Yeah, there are a lot more after that, but they're all like the proposal that Lauren was asking me about, that I'm the PI for, they're all like phase A studies that are not funded for flight yet, or concepts that they're all basically just things that haven't been funded yet, but we've submitted lots of proposals. So I didn't list any of those things that haven't been selected for flight, but we do have probably about the same number of missions. If they all win, we're going to be even busier than this.
And any trends in there? Like, do you guys want to build heavier things, or back to the roots and single unit CubeSats or something? Like, no, of course not. But
it's basically becoming everybody's doing 6U. I don't know of any that are 3U anymore or smaller. I think still the only 12U is the Sprite one that I talked a little bit about. So I don't see them getting bigger or heavier or anything. And the other trend that I don't yet see, but that I'm hoping to see and contribute to, at least in the medium term, is constellations. Because that's like, there's a lot of power in constellations, and that can really only be unlocked with CubeSats, or at least with small sats.
yeah, so then orbit control as well?
Yeah, we don't have any that are doing any kind of propulsion things. I mean, through InspireSat, which I think probably some of you are familiar with, we have some that I think Amal has been planning on doing some thruster tests and things.
Right. IS-4.
Right. But I don't know that there are any at LASP that have been proposed or upcoming that require any kind of or orbit maneuverability. Though I know that at least in heliophysics, there's a ESA mission called Proba 3, which is going to be, so I think that's like the order of 100 kilograms. So it's roughly a small sat. And that's going to be doing a really cool mission where they're going to be doing a coronagraph looking at the sun. But instead of just putting a disk on the front of their instrument, they have a separate spacecraft that's flying out in front. And that is the occulter. So they can get a really huge baseline, which basically eliminates the diffraction. That is a huge challenge for instrument design. So we do have one person at LASP, Phil Chamberlain, who's proposed that same concept, but as a CubeSat, and you would kick out, instead of a spacecraft acting as the occulter, it would just be a black ball, so it would be completely passive. And I don't know if he's proposed that to anything yet beyond like internal research and development, but it is something I know has continued interest in exploring, and maybe he will propose that at some point.
Yeah, no, that's well, what you mentioned with Proba and things. That's a very different class of technology. It's that's old space technology, not some not CubeSat style technology. So.
Yeah, I didn't even mention
orders of magnitude more budget and things like that. And development times that are probably going to be like 10 years or something.
Yeah. So there is like I've worked on a bunch of CubeSats, but the one that I did not work on, but despite that is my favorite CubeSat of all time, is JPL did the Marco mission, which was 2 6U CubeSats that flew on their own to Mars. So they like did the thrusters and everything, and it worked. And that's still baffling to me that like that's actually happened in reality.
I still remember the glare at the excitement in the eyes of the people who presented it like 2 years at SmallSat. Yeah, they were very happy about that. Okay, thank you very much for your answers. Cool.
So James,
thanks for your questions.
With all these new LEO communication satellite constellations like Starlink coming up, do you see the potential for increased use of these constellations for, say, increased data rates from LEO missions?
I can't say definitively. I could say I hope that happens, and for low latency as well. Mm-hmm. So the problem I've heard is that you need to be under them. Like this is the same problem we've had with Globalstar in the past, is that they're like barely above your LEO CubeSats, and so the cone that they're looking down is designed so that on the ground that cone is wide enough, the circle that reaches the ground, that there's overlap between them. But if you're right next to them, just barely under them, there's big gaps in between those cones. And so you get lots of communication blackouts, and it makes it unreliable, and that's caused problems with Globalstar, we think, for some of the missions. And I don't know if that'll still be the case with Starlink or not. I hope not, because that would be some amazing technology to leverage.
Definitely. So let's see, are there any other questions from the audience? Again, please unmute yourself and start talking.
Yeah, this is Wing Yip.
Oh, yep. Hi.
I want to ask James, you know, I look at your table, it looks like that basically it says that the life cycle of a CubeSat mission is something like 2 to 3 years, right? I mean, because you haven't even started it. You propose, you're waiting for things, you know, happening in 2024, 2023 to start. So during this short cycle, you know, I mean, usually for regular normal satellite projects, you have different kind of steps of review process. And how would you do that? You know, I mean, with this CubeSat, I mean, you do it all by yourself by just taking photos, or how do you check?
Across a multi-year program?
Yeah,
I guess.
I mean, like the one that you just mentioned, you know, like a CC. I mean, those are old ones. Those one to be launched. I mean, the one most recent one, you know, you're working on.
So yeah, those are. We want them to be typically like 3-year time cycles, so that particularly the ones that involve students, so that it's easy to fit them into at least a PhD, and hopefully as close to a master's student being able to be involved in a majority of it as possible, and then they can carry the documentation along with them. But in practice, they tend to stretch out a little longer than that. But still, I don't think we've had any that have stretched beyond like 6 years. So if a PhD student started in the beginning, they would see it through to the end if it was timed right. So yeah, I think timing usually works out. And some of these missions upcoming that we have don't involve students at the same level. They all still involve students, but they've been moving, at least some of them, more towards dominantly being professionals, in which case the professionals are applying what they're used to, the standard for bigger missions of doing documentation and things to those missions.
So you don't have things like a preliminary design review and the end you have the critical design review, that kind of thing.
Yeah, we still do all of those. I mean, even though NASA doesn't require us to do them, even for the smallest projects like CSSWE was less than $1 million, we still did all of those design reviews because it's good practice and it's good education as well for the students. But that does also leave a documentation trail. That's actually a good point. I should have mentioned that. It's not just all photos and a PhD student carrying the load. It's routine things like all the design reviews. And
who will be the reviewers?
So that's one area where it's really easy or much easier at least, to get mentors to come in, because all they got to commit to is a couple hours every few months, and so they're experts in whatever their field is, electrical engineering or systems engineering or whatever, and they'll just come to the review, provide their feedback, and then let the students follow up with them if they have questions later. So the ones that are more interested will be more involved throughout the semesters, but those that don't have the time and are overcommitted already, et cetera, or aren't that interested in interacting with students, some of them, they'll just come to the design review and drop off their feedback. Yeah, I mean, with Colorado, of course, easy, because just make a phone call and you get people, sitting around. And I think that in NCU, I mean, I'm talking to Roland, that you might have to get some help from outside, right? Yeah, we've done that too. It's been like 95% people, just engineers at LASP, but we don't cover every expertise, so we have pulled people from outside as well.
And I imagine working on a spacecraft, well, sorry, I don't have to imagine, but in a spacecraft project, it's quite different in a sense working on a typical, say, PhD project where you have stricter time constraints and heavier level of responsibility. And I'm just wondering, just to students who are just coming in and maybe contemplating the possibility of getting involved in a satellite program, do you have any advice in terms of how it is similar to what you would expect for a normal PhD and how it isn't, and any advice there?
Yes, the one piece of advice that's, I think, critically important that was given to me by my PhD committee years before I was, defending, is not to hinge your PhD entirely on the success of the mission, because lots of things can go wrong. So have something else going on the side that will be sufficient to make sure that you satisfy all of the more stringent requirements to obtain the degree. Otherwise, you could get, depending on how strict everything is, you could be stuck in grad school for a decade.
Funny, I think I heard the same thing regarding New Horizons.
Right. So that's the biggest fear, and I think it's prudent. And it's typically not too hard. There's usually something else going on where you can focus on more science or some sort of other engineering thing. Yeah, so I would say that's the most important piece of advice. And the second one is just like, this probably doesn't apply to everybody, but it applied to me and a lot of the other people I know, is to use it as an excuse to broaden your experience. Like, just because you don't know how to do mechanical design in SolidWorks or ANSYS or whatever software you're using for CAD, like, pick it up. Like, just open the software and start playing around with it, and like learn the tools and ask people that do know those things around you for help and guidance. And I think that's very valuable for discovering what things you do enjoy a lot. And then if it turns out you don't, or it turns out you end up in some other field, like you end up as a systems engineer or something, it'll make it so that you can communicate with those people that are domain specialists in electrical engineering or whatever better than if you had very little idea of what they do and how they do it.
It's very good advice. I think we have time for one more question. Joe?
Could I ask a question to James? This is Joe Fong.
Hi.
Hi, James. Sorry I missed most of your CubeSat presentation, but I have a question related to PC104. PC104 is one of a standard for building CubeSat and StackUp. But how about the CU's program? Are you all using that, or what is your opinion on to using the PC104 standard?
The nice thing about PC104 is that because it's a standard, there are lots of COTS components that you can get. You could build a whole CubeSat without having to do anything but PC104 and just buy everything off the shelf. So that's really nice. So we try to take advantage of that in some cases, like on, I think we're doing this on InspireSat 1, where we can leverage the wide availability of things in PC104, but get around the downside, which is the thing I described with CSSWE, where if something goes wrong with the middle board in the stack, you have to disassemble the whole thing to do anything with that board, and then assemble it all again, and then run your test again, and it's very cumbersome. So what we're doing when we can't get around PC104 now is like taking that one board and just connecting it to one of our boards, which is a daughter board that slots into the backplane of something else. That way we can still get access to the COTS part, but we don't have to be limited by the stack, basically.
Okay, and I guess we have time for one final question from Jose. Jose, can you go ahead?
Hello, Dr. Mason.
Hi.
I'm seeing here your timeline that from 2021 and in the future you have many simultaneous launch. And you've mentioned that you have achieved a lot of maturity regarding the space system design. So can we assume that your development, I mean, those satellite developments right now are more divided into smaller teams, or what do you think is the reason that you have achieved that level of maturity in order to be able to, by the assumption that I have from your timeline of designing so many satellites in I think a really short time lapse?
Yeah. So basically is primarily stemming from this CTIM one here at the very top. That's basically the 6U evolution of the Minx bus. So we've got a COTS attitude control system from Blue Canyon, and we've now got a 6U bus that's been designed. to handle everything. So basically all of these now are just taking the CTIM bus and putting a different instrument in it.
Okay. Thank you.
Okay, that's about all the time we have for this session. So thank you very much, James, for staying up. What is it, 8 p.m. right now?
Almost 7 p.m.
7 p.m.
So not late.
Okay, not bad, not bad. Okay. So, well, thanks a lot for presentation and for the discussion. Best of luck on the new spacecraft.
Yeah, thanks. And thanks for having me here as well. And thanks for all the questions.
No problem. And looking forward to catching up with you, hopefully in person, hopefully sometime soon.
Yeah, fingers crossed.
All right. Stay safe, stay healthy.
You too.
All right.
Bye,
thanks.
everyone.
See ya.